Okay, today also we will discuss Poisson brackets. Okay. All right. So we discussed some properties of it, and we said that we can actually do problems without remembering the definition because we know the properties of it. All right. And such properties, it's actually properties, some of the properties that we discussed, they correspond to a property of what's known as Lie algebra. Okay, you don't have to remember it, but the Poisson bracket is a Lie algebra. All right, it's Lie algebra. You can say it's a representation of Lie algebra. Okay, commutator is also a Lie algebra, so that's why there is a deep connection between Poisson bracket and commutator. Okay. All right, we looked at some of the important properties, and another important property is this. Okay, if you have u comma qi, all right, you can see that you can just check with the definitions, and you'll see that this is equal to minus dou u by dou pi. This is obvious, right? Because there will be derivative of this with respect to q and of this with respect to p, all right, and that will be 0. Okay. And minus derivative of this with respect to p and derivative of this one with respect to q. So the only term surviving will be minus dou u by dou pi. All right. You can check it. You can prove it as a homework. Okay. And we have got u with pi is equal to dou u by dou qi. All right. So this means that we were talking about. Let's just put it in a sentence. Okay, so we'll use square bracket here onwards, all right? We can also use curly brackets. You just define the notation in the beginning. Okay, I may just mix it up a little bit in between, then you can just correct me. Or it doesn't matter, you know that these are the Poisson brackets, okay? In the notes, I'll put it consistently. All right, so u with v, right? We are talking about u with v, the Poisson bracket of u with v. And if one of the functions, okay, either u or v, one of the functions u and v, okay, is one of the coordinates. Okay, suppose either u or v is one of the coordinates or one of the momenta. Okay, then the Poisson bracket reduces to a partial derivative. Okay, this is a good result. So if you look at this, for example, okay, some function with respect to pi. Okay, so we already saw that if you have the Hamiltonian, okay, and if u does not depend explicitly on time, this is simply dou u by, sorry, if you, this is equal to, I'm sorry. We saw that for Hamiltonian, this relation holds, du by dt is equal to u with h, all right, if u does not explicitly depend on time. And we said that Hamiltonian is the generator of time translations, right? So in this case, what we have here is you've got u with pi and you get dou u by dou qi, right? So you get dou u by dou qi, the derivative with respect to space. So from here we can say that momentum, okay, momentum is the generator space translations. Okay, and if it's an angular momentum, it will be a rotation, etc. But here we are talking about this momentum. Okay, so we can say that momentum is the generator of space translations. But we'll see these things in more detail when we discuss canonical transformations. Okay, so this is a good result that you can keep in mind. Sometimes it will be very useful to solve some problem. All right, if you have a function with qi or pi, it's just a partial derivative. You don't have to do all the steps. Okay, it's just a partial derivative. You just have to remember the sign here. If it's with qi, it's minus dou u by dou pi, and if it's with pi, then it's dou u by dou qi. It's easy to remember because you know that if pi comes on the second place, okay, if pi comes in the second place, then this is just a space translation. All right, this space translation. I mean, we know that this is a generator of space translation. So this will come with a plus sign, dou u by dou qi, and that will be with a minus sign. Okay. Some problems, okay, you can quickly solve using this method without going into all the steps. Here is another important property. If you have dou by dou t of u with v, okay, or some functions, phi with psi or something, let's just say u with v, okay, this is equal to dou u by dou t with v plus u with dou v by dou t. Okay, this is an example. We didn't prove all the properties I asked you to prove. We'll do this in the class. Okay, dou u by dou t. So this looks like the product rule, right? So if you have this looks like the Leibniz rule. If you have the derivative of a product of two functions, then it's the derivative of first function multiplied by the second function and plus etc. Okay, it looks the same form. Let's just prove this. We'll use the definition of this thing. Okay, dou by dou t of uv. Okay, this is equal to dou by dou t of. We'll assume Einstein's summation convention. So this is dou by dou t of dou u by dou qi, dou v by dou pi, okay, plus sorry, minus dou u by dou pi, dou v by dou qi. Is that correct? Yeah, we have just applied the definition of what do you say, the Poisson bracket, okay. So this is equal to, so this is just a derivative, right? Since it's a partial derivative, we can exchange it with the other derivative. If it's a total derivative, you may not be able to do that. But if it's a partial derivative, we can always exchange it with the other partial derivatives. So let's immediately write this thing as this equal to dou by dou qi of dou u by dou t. Now you are using the product rule. Okay, you have to take the derivative of this multiplied by this plus this multiplied by derivative of this, and then we can interchange t and this coordinate. That's what I am doing. First, I'm taking derivative of the first function with respect to time, partial derivative, and I'm interchanging q and t. That's after that, those steps, I get this term. Is that correct? And this term remains the same. Okay. I hope this is clear. We don't need further explanation, right? Plus, okay, now what you do is that you keep this one constant, dou u by dou qi, and then you take dou by dou t of dou v by dou pi, right? But dou by dou t of dou v by dou pi is dou by dou pi of dou v by dou t. So this you can write as dou by dou pi of dou v by dou t. Okay, and also you have these terms here minus. You do the same thing, all right? Dou by dou pi of dou u by dou t, and you have got dou v by dou qi minus dou u by dou pi dou by dou qi of dou v by. You all can see the board, can't you?
Yes.
Okay. All right. So now you just rearrange these terms. All right. This is dou by, so let's just combine this dou by dou qi of dou u by dou t, dou v by dou pi minus dou u by dou pi. No, let's combine it with this. Let me see which we need to combine. This is, yeah, we'll combine it with this. All right. Okay, so this is nicely written. So we can combine these two terms. And what does these two terms give? Okay, this is dou by dou qi of dou u by dou t, dou u by dou pi minus dou by dou pi of dou u by dou t, dou v by dou qi. All right, so from the definition, you see that this is simply the Poisson bracket of dou u by dou t with v. Is that correct? All right, you have got two functions. So you take the dou by dou qi of the first function dou v by dou pi minus dou by dou pi of the first function and dou v by dou k. All right. Similarly, these two terms, okay, these two terms will give this is dou u by dou qi and dou u by dou pi. So this is u with, and this is dou by dou pi of dou v by dou t, dou by dou qi of dou v by dou t. So that's equal to u comma dou v by dou t. Okay. So this result is useful. Okay. All right. So let's do another problem now using this result. Okay. Now let's do another problem using this result. We are going to prove that d by dt. Okay. So far we were looking at the partial derivative. Now we are looking at the full time derivative. Okay. Of u with v. This is equal to du by dt with v plus u dv by dt. Okay. Now this may look rather simple, okay, because we did for the partial derivatives, but the proof is not very simple, right? You really have to prove this because this should not be obvious. Like, it looks obvious, it looks like the product rule, but we cannot interchange. In the previous problem, we interchanged the partial derivative and the partial derivative with respect to t and the partial derivative with respect to q and p. Am I right? Here we cannot interchange the partial derivative with respect the full derivative with respect to time and the partial derivative with respect to q. You cannot interchange that. Okay, so you need to be more careful. So how do we proceed for this problem? Okay. All right. So we know that we need to find d by dt of u with v. Okay, so we use the basic definition using the Hamiltonian. You have to bring in the Hamiltonian. We know that d some function df, let's say df by dt is equal to, if f is a function of q, p, and t. All right. So this is equal to, we showed that this is equal to f with h plus dou f by dou t. Am I right? Okay. So we have to use that here. So this means that we know that u comma v is a function, some function. Okay. So in place of f here, we have u comma v. So d by dt of u comma v. Okay. What is this? This is equal to h comma, sorry, you said this is f comma h. So this is u comma v with h, am I right? Plus dou f by dou t. So dou by dou t of u comma v. All right, is this step fine? Okay. Now what do we have in the result? We have a du by dt and dv by dt. Okay. So du by dt will involve u with h and dv by dt will involve v with h. Okay. So we need to write this in a more convenient form. What we'll do is that we'll use the Jacobi identity. Okay. For some problems, this using this identity might be very useful. Okay. All right. All right. So what's the Jacobi identity? Jacobi identity says that uv with h plus, right? So you take the cyclic permutations, right? Let's take this as 1, 2, 3. Okay. 1, 2, 3. What's the next is 2, 3, 1. So you'll have VH. Let's first write the permutation, right? 2, 3, 1. So VHU. Okay. VHU plus 3, 1, 2. These are the cyclic permutations. It's 3, 1, 2. So it's HUV. Am I right? 3, 1, 2. HUV. And we started with this here. So this is like that. This is equal to 0. This is what the Jacobi identity says. Okay. So what we need here is UV with H. Okay. So we see that UV with H is equal to minus VH U minus HU V. that correct? Yeah. Okay. Now you substitute it back here. Now we substitute it back here. What we need to find is this. So d by dt of uv, this is equal to, okay, instead of uv with h, we have minus vhu minus vhu minus hu and v, okay. All right. Now we know that these things are antisymmetric. So we can write this hu as minus uh. Am I right? Okay. So when you interchange two functions inside the Poisson bracket, then you will get an extra minus sign. So we can do that here because we like this v with h. So we'll write it as plus u with h. Okay. So any constant inside the Poisson bracket, we can just pull it out. All right. So this is UH comma V plus dou by dou t of UV. Okay. All right. Now what do we do? What do we do now? So these results, all right, you may not be asked to prove this, but you may be asked in the options, all right, which among the following is correct, etc. Okay. And they can give really confusing options. Okay. Now, what is this? We know that dv by dt, right? dv by dt is, what did we say? It's v with h plus dou v by dou t. Am I right? So we have this. We know the partial derivative of u with v is, and it's better to write this in terms of the derivative. So this we can say that v with h. Okay, v with h is equal to dv by dt minus dou v by dou t. Am I right? Can we do that? Yes. Okay. Similarly for here, u with h you can write as du by dt minus dou u by dou t, or partial derivative with respect to time. All right. Now using this we get d by dt of u comma v. You have to be careful not to miss any minus signs. Okay, often we miss a minus sign. Okay, I miss a minus sign usually. I hope I haven't missed anything. So let's check. This is equal to minus. All right. We've got v with h comma u. So v with h is dv by dt minus dou v by dou t, comma, right, comma u. Here we've got plus, this is du by dt minus dou u by dou t, comma v. Okay. Now let's just write this term like this. Plus, we know this result. This is equal to dou u by dou t, comma v plus u dou v by dou t. Can we simplify now? All right. Yeah. Now, okay, this minus sign, we can write this thing as this equal to so how do we easily simplify this? Let me just check. Okay, I think we can. This, let's just write one more step so it becomes easier. So this we'll write it as u comma dv by dt minus dou v by dou t Okay, so we have taken away the minus sign by interchanging the terms inside the Poisson bracket. Okay, and this we'll write it as plus. Okay, we've got v in the second place, so no problem. We'll do this like that: du by dt minus dou u by dou t, comma v. Okay, and plus. Okay, we'll take this term u comma dv by dt plus this is du dou u by dou t, dou u by dou t comma. All right, now it's a matter of just combining these terms. Now we have already seen this particular property. Okay, we are using many properties of the Poisson brackets. All right, we have seen this property that if you have u with v plus w, right? We saw this. This is equal to u comma v plus u comma w. We said that it follows a distributive law, right? So here you see that this is u comma something plus u comma something else. So that's equal to, this is u comma, yeah, let's say this is a and this is b. So this would be u comma a plus b, am I right? So this is equal to, we'll see. So we use this idea. So u comma v with u comma w, you can write just u comma v plus w. So in that way, we can combine these terms. We see that d by dt of u comma v is equal to. So if you combine this, this is equal to u comma, all right, dv by dt minus dou v by dou t. So this is dou v by dou t, right? Okay, so this dou v by dou t and this dou v by dou t will cancel. What you have is u comma dv by dt plus, okay, this is du by dt minus dou u by dou t plus dou u by dou t. So these two terms also will get cancelled. So this is simply du by dt comma v, right? So we have actually proved that d by dt of u comma v is equal to du by dt comma v plus u comma dv by dt. All right. Now, even though it looks like the same result of the partial derivative, you have to remember that it's also because of the property of the Hamiltonian. All right. We had to use this relation. This is not really obvious. All right, because as I said, we cannot interchange the full derivative and the partial derivative. Also, this is because we use this property. Okay. H with v, v with h, or dv by dt. We had to use this property, right? dv by dt equal to v with h plus dou v by dou t. If this property was not true, then this result is also not true. All right. So this is not it's not an obvious result. We have to use this particular property. Okay. All right. So this is a good result. This can be asked. And when we solve problems, all right, now we know we don't have to remember the fundamental definitions. Okay, we know all the properties of the Poisson brackets. Right? We have studied all the properties. You can take them as an axiom, okay, axiomatic system defining classical mechanics, which means that some of the properties that I have given in the beginning, all right, about the antisymmetry, about the linearity, the distributive thing, etc. All these things and how it behaves when you multiply by a constant, that comes under linearity. All right, and all these things together, we can say that these properties define an algebra called Lie algebra, or defined Poisson bracket, or these relations are true. And then we also define the fundamental Poisson bracket, right? This Q, we also define Qi with Pj is equal to delta Ij. And all these things we can consider as an axiom, an axiomatic set, axioms of classical mechanics. All right. So you can develop classical mechanics purely from these axioms. So you don't need to know anything else. Okay. From all these axioms alone, including this, okay, you postulate this Poisson bracket, and all of classical mechanics can be developed from there. You don't need to know the fundamental definition. All right. If these axioms are satisfied, then classical mechanics or all of mechanics can be derived from them. That's known as an axiomatic system. Right? We can do that in quantum mechanics also. We can derive all of quantum mechanics just by assuming the commutator, right? We just need to assume the commutator x with px is equal to IH cross of x, let's say xi with pi is equal to IH cross delta xi with pj. Right? We just need to postulate this commutator and all of quantum mechanics will follow. You also need to give axioms for the properties of the commutator, but the properties of the commutator are the same as the properties of the Poisson bracket that we gave. All right, linearity, distributive, how it acts when you multiply, it's all the same. All right. So instead of let's say Qipj is equal to delta ij. If you use this along with other axioms, you get classical mechanics. And if you use this Qi with Pj is equal to IH cross delta ij, along with the other axioms, you get quantum mechanics. All right. So the only difference is in this fundamental bracket. This is Poisson bracket, this is commutator, but the only difference is in this fundamental bracket. All other properties are the same. Okay? That's why this is an elegant formalism, and it in a way it unifies the mathematical framework of classical mechanics and quantum mechanics. All right? So it's a good thing to try to solve problems without involving the definition of Poisson brackets. All right, it's okay. Sometimes using the definition might be much easier. For example, I gave you this u with pi is equal to dou u by dou qi. These things can be used. Okay? You have to check. Okay? But at least you should be able to solve these problems without remembering the fundamental definition of Poisson brackets. All right. We had done one problem in the last class. We wanted to find the Poisson bracket of r vector modulus of r vector modulus of p vector, right? And I used the fundamental definition, and it's not very satisfying to use the fundamental definition. So let's check if we can solve this problem without invoking the fundamental definition. You'll see that this might even be easier. You just have to think a little bit. That's a good thing, all right? So this is actually modulus of r vector is square root of x square plus y square plus z square. Okay, I'm just giving you two different methods of solving the same problem, all right? And this is square root of px square plus py square plus pz square, right? This is what you mean by the modulus. Now the square root is not really nice. Okay, we cannot really deal with the square root like that. So why don't we just square it? Right? So we'll try to get a result here. Suppose you have u square with v square. Okay, what's its relation with u comma v? If we find that, we can use this. Am I right? Okay. Suppose you have two functions u square and v square. Right? What's the relation with u comma v? We just need to check this. All right. So first, let's get a few good results here, which can be used. Suppose you have got u comma v square. Okay. Using the properties, you see that this is equal to u comma v multiplied by v plus u comma v multiplied by v. All right. In quantum mechanics, this order is important. You cannot write it like this. One v will come here and the other v will go there in quantum mechanics. All right. Classical mechanics, no problem. You can write it like this. So this is equal to 2v u comma v. Right. So this result is good. We may be using, we already used it for one problem in the previous class. And it's really easy. Okay. If you forget, you can just try and find it. Okay. So using this, we find u square with v square, right? U square with v square. So first let's do this. This is equal to 2v u square with v, right? We just used this formula for v square alone, all right? So it's equal to 2v u square v. And now what's u square v? That's equal to 2v multiplied by u square with is u square v is 2u uv. Am I right? So this is equal to actually 4uv u with v. Or we can say that u comma v is equal to this. What we found is u square comma v square. We can say that u comma v is equal to u square comma v square divided by 4uv. Am I right? Is this all right? Is this okay? This is purely for classical mechanics. All right. In quantum mechanics, this doesn't make sense. Is this okay? Right? You can remember these relations, and these are really useful. It's not very difficult to remember these things, right? U with v square is 2v, u with v, and u with v is u square v square by 4u v. All right. So why do we have this? Now we can find just u square v square. Okay, we can find the commutator of the square of these things and just find the corresponding commutator of the square roots. Right. So that might be the easier method. Are we fine with this? I'll just write down our results here. We've got u with v square is equal to 2v uv, and we've got uv is equal to u square v square divided by 4 uv. Okay. All right. So what does this mean? We need to find this commutator. So we'll take it as u square comma v square, right? X square plus y square plus z square, comma px square plus py square plus pz square, all right, divided by 4uv. So that's equal to 4. What's u? Square root of x square plus y square plus z square. And what's v? Square root of px square plus py square plus pz square. All right, this is the commutator of modulus of r vector with modulus of p vector. Okay. All right. Okay. Now this is really easy. Okay, you see that once you are familiar with these things, this is really easy. All right. You need not take all the Poisson brackets. You just need to take the non-zero Poisson brackets. And you know that the only non-zero Poisson bracket are between x with px, y with py, and z with pz. All other Poisson brackets are 0. X with py is 0. We've got this result, right? Qi with pj is equal to delta ij. All right. If they are both x, it's 1. If they are I and j are different indices, then it's 0. Which means that x with px is 1, x with py is 0, x with pz is 0, likewise. But y with py is also 1. That we can use. So we don't have to do all these things. All right. So what we have just is x square comma px square plus y square comma py square plus z square comma pz square. We just used all other combinations are 0. Now this we can write. This is 4. This is simply modulus of r vector, modulus of p vector, right? This modulus of r and modulus of p. And what's x square px square, right? All right. What's x square with px square? We can just we can use this, right? U square with e square is equal to 4uv multiplied by uv. Am I right? So this is equal to 4x px multiplied by x comma px. All right, that's 1. Similarly, this would be 4y py plus 4z pz divided by 4. Okay. Now what do we have here? For x px plus 4y py plus 4z pz, this is nothing but for r vector dot p vector, right? R vector dot p vector is x px plus y py plus z pz divided by 4 modulus of r modulus of p, and this is equal to 4 and 4 gets cancelled. This is equal to r vector divided by modulus of r vector multiplied by p vector divided by modulus of p vector. Okay, and what's that? That's equal to r cap dot p cap, right? Because this is the definition of the unit vector. The vector r vector divided by the magnitude of it, that gives you just the direction r cap, and the vector p vector divided by the magnitude gives just the direction of that momentum, that we write it as p cap. So the answer is r cap dot p cap. Okay? So I just wanted you to show that using some tricks like this, we can avoid the basic definition altogether and just do it purely algebraically. And this is good. Okay, this is a good thing to practice. Right. It need not be so lengthy. All right. Once you get used to some of the relations like that, you can do that in a few steps. Okay. Do we have another problem? All right, that's correct. So let's do some other interesting problems. So in one of the previous classes, we got the Hamiltonian for a particle, charged particle in an electromagnetic field. Right? We did not find the equations of motion. Right? So let's find the equation of motion using the Poisson bracket. This is easier than the other one. All right? So let's say H is equal to 1 by 2m. We had the Hamiltonian was 1 by 2m. Pi minus q ai square plus q phi. All right. Now we need to find the equations of motion. All right. Okay. So let's first find xj dot. Okay, xj dot is equal to, we know that this is equal to xj with h, the commutator of xj with h. Am I right? This is the thing that, because there's no explicit time dependence. All right. Now this is equal to, so we write xj with 1 by 2m pi minus qai square. There's a sum. Okay, I'll pull the summation outside. You can do that. All right. Plus q phi. Okay. I'll also pull all the constants outside. All right. This is equal to summation over I 1 by 2m. We can pull the constants outside of the commutator. This is xj with pi minus qai square plus q phi. Okay. Now, if you know that, if you notice that this phi, it's a function of only the coordinates and not of the momentum, right? It's always a function of coordinates. So xj with phi will be 0 because this involves only coordinates. So if it has to be non-zero, did I tell you that all these commutation relations are 0? I think I should have included in the notes. Okay, I thought it's obvious. So yeah, we said this because yeah. Anyway, xi with xj, pi with pj, all are equal to 0. All right. Only xi with pj is delta ij. Okay? So these don't have any terms there. It's gone. So this is equal to summation over I 1 by 2m. We have got this in the form u comma v square, right? And what was our result? That's equal to 2 multiplied by v pi minus qai, all right, multiplied by xj comma pi minus qai. Is that right? Okay, we used the result that we obtained a bit before. We had u comma v square is equal to 2v multiplied by u comma v, right? Okay. So this is equal to 1 by m summation over I, all right. This is pi minus qai, and xj with pi, it's delta ij, right? Xj with pi is delta ij. You have to write delta ji, but this is symmetric, so it doesn't matter. I'll write delta ji. Okay, this is symmetric, so that doesn't matter. Delta ji. And what's xj with ai? Right? What's xj with ai? We know that this. Yes, correct. Okay, we know that this a also is a function of coordinates and time alone. So that also gives you 0. All right. So this is equal to xj dot is equal to, you have to sum over I. Okay, you have to sum over I, but the only term that will survive is the term with I equal to j. So this becomes pj minus qaj. The summation is gone. The Kronecker delta is also gone, divided by m. Okay, this is xj dot. Xj dot was the component of velocity, right? Yeah. Okay. So this is this is enough. I think we can stop at this stage, or we can write v vector is equal to p vector minus qa vector divided by m. All right, in the vector form. This is the component, and this is the full vector with all the components. Okay. All right. Now we can also find Pj dot. Pj dot is equal to Pj with h, okay, and that's equal to 1 by 2m. Again, the summation, everything I'll pull out. 1 by 2m, summation over I, Pj with Pi minus Qai square, okay, plus Q phi. Here you have to be more careful, right? Okay, because these terms are non-zero, right? Because this A involves the coordinates. So P with A is non-zero. Phi also involves coordinates. So phi with Qj is also, so phi with Pj is also non-zero. So this we can write it as 1 by 2m. Again, we'll use the rule that we had, Pi minus Qai, okay? Because this is square, right? We also will separate the terms. We have got Pj with Pi minus Qai. Okay, we've got one more term. We've got one more term. So let's just write it out separately. 1 by 2m summation over I. We also have Pj dot Q phi. Okay. Oh, I think I made a mistake. So this since this Q phi is there, this 2m cannot be pulled out. Okay, so this 2m will come here, and this 2m will go there. Okay, then it's correct. All right. Okay, so this is equal to, I think we'll have to just write it like this. All right, this Pi minus summation over I, Pi minus Qai. Okay, Pj with Pi is 0, right? So we have a minus sign here. We only have Pj with Qai. I think I can also pull out the Q here. So it's Pj with Ai. You also have a 2m, right? Am I right? Okay. Pj with Ai. Okay, the minus sign and Q by 2m I pull outside, plus 1 by 2m summation over I. Pj with Q phi. Again, Q I can pull out, Q by 2m summation over I. This is simply Pj with phi. All right. So in this form, we can find the equations of motion. We can stop at this point, all right, because we don't know the exact functional dependence. Okay. Now you can play around a little bit and see that this is equal to the usual result that we have, the result for Lorentz force law. All right, show that. You need to do a little bit of algebra, rearranging terms and maybe adding and subtracting something. This becomes Lorentz force. Okay, but in commutator form, this is the point where we need to stop. Okay, if we know the exact functional dependence phi and a, then we can continue to find it. All right, maybe we'll write it a little bit more nicely. This is equal to summation over I. We have got Q divided by 2m taken outside. Okay, and then you have this Pi minus Qai multiplied by Pj with Ai. Okay, plus Pj with phi. Right, that would be the final answer using the Poisson brackets. All right, okay. Next thing we have is the angular momentum Poisson brackets. Let's also do the angular momentum Poisson brackets and then stop. Okay. I had it somewhere here. All right. This will be useful later on. Okay, these things we need to use later on. So find the Poisson brackets find the Poisson brackets, Lx with Ly, okay, where Lx and Ly are components of angular momentum components, okay. All right. So we could actually find the general result. Finally, we are supposed to come to the general result, Li with Lj. What's Li with Lj? What's the Poisson bracket of two angular momentum, simply two angular momentum. All right. Can we write a general form for that? So let's start with Lx with Lx and Ly. We know that L vector is equal to R vector cross P vector. All right. So Lx is equal to, we can either use the Levi-Civita symbol, or we can use the determinant form. And you know that Lx is equal to y pz minus z py, right? I hope I don't have to prove this. We can do it like this, or we can use the determinant form. All right, we know that Li is equal to epsilon ijk, all right, epsilon ijk rj pk. What we need is L1, so we need, this is epsilon 1 j k r j pk. And as I said earlier, once we fix this one, this j and k can take values 2 and 3. So this is epsilon 1 2 3 r2 p3 and plus epsilon 1 3 2 r3 p2. So we can use the property of the Levi-Civita and see that you get a minus sign here. Okay, by y we mean it's r2. Okay, for pz it means p3, etc. So you can just go around like that. Okay, and what's Ly? In the similar way, you can find Ly is equal to zpx minus xpz. Okay. All right, zpx minus xpz. You see that if you write it like this, Lx equal to, then this comes in cyclic permutations, right? xyz and minus xzy, something like that. All right. If it's a cyclic permutation, you get a minus plus sign or a minus sign. It's easy to remember this. Now let's find. Similarly, we also have Lz is equal to xpy minus ypx. Right. So what's Lx with Ly? Lx with Ly is equal to, you just do this. It's ypz minus zpy. That's Lx. Okay, comma. Ly is zpx minus xpz. All right. Okay. Now you can be careful again. At first, I think we'll just write down all the terms. Okay, this is equal to ypz with zpx. You just use the distributive rule. Ypz with zpx. Okay. Plus, sorry, minus. There's a minus sign here. Minus ypz with xpz. Am I right? Okay, and just distributing this one with this, and the same thing with the second term. Plus, minus, we have got zpy. Now you combine zpy with each of the terms, with zpx, okay, and plus, because minus and minus, zpy comma xpz. Okay. Now you can see that some of the terms are 0. Am I right? Now, if you look at this term, it has got y, pz, and zpx. Is there any non-zero combination? Y with z is 0. Y with px is 0. But there's pz with z. Okay, that's only non-zero combination. What about this? You got y with x, that's 0. Y with pz is 0. Pz with x is 0. Pz with pz is 0. So this term will be 0. Okay. What about this term? We got z with z, 0. Z with px, 0. Py with z, 0. Py with px is also 0. Right. So we've got only we've got only these two terms. All right. And let's start with this ypz comma z px, which is the only non-zero combination. We have got pz with z. All right. So there are many terms here. We have to take y with z and pz So this when you multiply this, it would be yz px pz. I mean y comma z pz px and y comma px pz pz z. That's all 0. Then you have got pz with z px y, right? Pz with z and y px. You have to multiply. And then you also have pz with px. That's also 0. So only non-zero term here is pz with z. Am I right? And you have to multiply with the rest of it, y px. Okay, so it's not very difficult. Plus, this is an important relation. Z py comma x pz. Okay, what's only non-zero term? It is z pz. Okay, so yeah, that you can write it as z comma pz. What are the terms that we left out? Z pz pyx. Okay, and this is equal to pz with z is -1, so minus ypx plus z with pz is 1. Let's write as xpy. Okay, we are doing classical mechanics. So this is equal to xpy minus ypx. And what was this? Xpy minus ypx is simply Lz. Okay, Lz. Right. In the same way, you can find all the other angular momentum commutations. Okay, you see that if it's with x and y, then the result is the z component. Right. If you have x and y, then the result is the z component. If it is similarly, if you have, so what we have is what we found is Lx with Ly is equal to Lz. Okay. Similarly, we'll see that Ly with Lz. Okay, that's equal to Lx, and you'll also find that Lz with Lx equal to my Ly. These are the cyclic permutations. If I'm so these are the cyclic permutations. It's all plus, right? If it's xy, you get a z, yz, you get an x, zx, you get y. Right? If they are the same, it's 0. If any two, if you take the angular momentum, the Poisson bracket of any same angular momentum component, that's equal to 0. And if it's in the different order, you'll have a minus sign. If it's Ly with Lx, it's equal to minus Lz. You can just see it from the Poisson bracket property, right? You know that it's antisymmetric. Ly with Lx is minus Lz, etc. Now, there's a very simple way of writing this down. You can use the Levi-Civit and simply write that Li with Lj. All right. This is equal to epsilon ijk. Epsilon ijk Lk. Right. This is a simple way of writing it. Summation over k is implied. All right. There's a summation over k. Now we can check this. What's L1 with L2? L1 with L2, we have got 1, 2 here. So you have to put epsilon 1, 2. All right. And the only possibility here, non-zero possibility in the summation is you have to put k equal to 3, right? Because if any two indices are the same, the Levi-Civita symbol will vanish. So it's epsilon 1, 2, 3, L3. Okay. This means that L1 stands for Lx, L2 stands for Ly. So this is equal to epsilon 1, 2, 3 is 1. That's equal to Lz. Similarly, you can get all the results from this simple formulation. So what you need to remember is this: Li Lj is equal to epsilon ijk Lk. Now, if you don't remember which is a cyclic permutation, etc., you just use this form. You know how the Levi-Civita behaves, and then this is the easiest thing to remember. All right. Okay. And angular momentum has a nice property, and I hope you already know about this epsilon ijk. I don't have to repeat the properties of it. Okay. If it's a cyclic permutation, it's +1. If it's some other combination, it's -1. If any two indices are the same, it's equal to 0, etc. And we have said that there was a summation over k implied by Einstein summation convention. Okay. Now, angular momentum has some nice properties when it acts on vectors. It's a bit special in that way, but we'll see that in the following sessions. We know that angular momentum conservation has to do with rotational symmetry or isotropy. So we'll also see soon that just like the momentum is a generator of space translations, angular momentum is a generator of rotations. We'll see that. Okay. So since vectors have specific rotation property, the Poisson bracket with vectors has a nice form involving epsilon I, j, and k. And we know that this L is also a vector in a way, right? It's not a full vector. It's called as a pseudo vector, but it has properties of a vector. Okay, some properties are like a vector, except for when you make a reflection or something, right? Okay. Yeah, we can continue in the next class. I think we have done almost everything using Poisson brackets. We'll use Poisson brackets also when we discuss canonical transformation. So it's a good thing to be really familiar with the Poisson brackets. Okay. All right. We'll also do Liouville theorem. We won't do the derivation. We'll just give the theorem. There are questions based on it. There are questions based on this angular momentum commutation relations also. Okay. All right. So are there any questions? Shall we wind up now?
Thank you, sir.
Okay.